Hello reviewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about DC electronic loads. So let's dive deep into it. So why do we exactly need this sort of stuff? Well, power electronics and power sources, be it battery, be it fuel cell, be it whatever, these things are key to our modern electronics. And be mindful, today's world will not survive if there is no electronics, like flat out. We cannot sustain 6 billion people without electricity. Like, it's not happening. So it's very compulsory. And not to mention renewables, we want to go into more renewables. They also need testing. You cannot just like, oh, I built a solar panel, it works. That's not how it works. You have to build it and you have to test it rigorously in order to figure it out. Will it actually survive? Will it actually work the way that you are expecting it to? So you have to be very mindful of these sort of things. And there is a very stark reason in reality why, even though iPhones are made in China, they are almost $3 trillion company versus all other Chinese brand. Why? QC. Because without testing, you are literally just relying on hopes and dreams. Like flat out, one factory can literally be manufacturing part for a first party manufacturer, and the same factory could be manufacturing something for basically a no-name brand, and output would be drastically different. Why? Testing. Many times whenever we look into the products of high name brand system, most of the time the money of course is for their profit, but there is a very significant proportion of it is going into QC stage. So let's say you said, hey, I built this power supply. Let's just say you build this power supply. How the heck do you know that this puppy will work or not? Will it give the power that you are demanding to? Will it have some hidden behaviors? And that comes the critical aspect of it. You need a way to expose hidden behaviors. For example, you may be like, hey, what happens if let's say this has multiple power rails? So it has 3.3 volt, 5 volts and 12 volt minus 12 volt, and those sort of power rails it has. It's awesome. But what if happens you have minus 12 volt, a bit of power draw on that, and you may have a weird scenario where it could unbalance your 3 volt, 3.3 volt. 3.3 volt could jump up to 5 volts. Now, like, wait, that's a very bad design. Yeah, that has happened. So, and that's the prime reason why every PC manufacturer will tell you, bro, cheap out on whatever hell you want to cheap out on. Never cheap out on this puppy. Never cheap out on power supply. So that's the reason for it. There are hidden behavior patterns. You may be like, without testing, you may be like, oh, this power delivery board, USB-C power delivery board is awesome. You load it up to, let's say, its maximum capacity, then it's like, wait a minute, it's supposed to give 36 volts output. It's only giving 32. What happened to the voltage? It's sagging and it's not cutting off. It's never supposed to sag. It's supposed to cut off. Under, like, same thing will happen with here. Like, let's say AC voltage that is coming in drops below a requirement level. Let's say it drops to 90 volts compared to, let's say, what is supposed to be 220 in case of India. It's not supposed to give you lower voltage into your component. It should be like, bro, no. So those are hidden behaviors. How would you test it if you do not have a way to load these puppies up? So that's why we invest money into this. And quality control is the difference between hulululu and actual product. So there is a genuine need for a device that can allow you to do expose all the hidden behaviors. So what's the logic behind it? Well, logic is you need a tool that can adjust its own parameter based on user input. I tell it, hey, draw this much amps until the voltage drops below a certain point. What else it needs to do, it will do it on its own. Like, I will say, hey, I'm connecting a battery to you, draw, let's say, 5 amps. Okay, go YOLO on 5 amps until the voltage drops below this threshold. Whatever the threshold may be, let's say the threshold is, 3.2 volts. Like, if it drops below that, you cut off. Okay, that's it. How the heck that's going to happen? That's not my problem. That's not user's problem. The parameters that needs to be set would be set by the device. So that's there. Now, the biggest hurdle in this sort of device is that it has to have a stable way of dumping the heat. What happens to energy? Let's say you're consuming energy. Let's say you are loading this puppy up. What does that mean? That simply means it consumes AC electricity, gives you DC voltage rails, and then you draw that power. Okay, this is completely loaded. That's awesome. But what happened to the power? Power is converted into heat. Now, heat has heating issues. Let's just put it that way. So you need a way to dump heat safely and efficiently. I'm like, wait a minute, what the heck heat dumping efficiently means? Well, here's the deal. You could design your electronic enclosure in such a way that the hot exhaust is very hot. Like, for example, same way we have blow dryer, not like heat guns, right? It could have like very hot exhaust, like a hot air station. That's not acceptable. Like, you have to design in such a way that it moves enough air that whatever the rating may be, let's say the rating is hundreds of watts, it should dump enough air into it that hundreds of watt heat going to the air does not mean air becomes like ludicrously hot. Air should not cross 100 degrees Celsius. Heck, I don't think it's legally even allowed to cross 60 degrees Celsius, unless, like, again, you can set it that, but then you have to have a giant yellow warning. It's like hot, caution, those sort of thing. So it not only has to have a way of taking that heat, it has to dump it safely and efficiently and without harm or fire. That's why fire part is very important. Yes, you can design in such a way that it heats up too much, but yeah, well, the device itself could be okay, but things around it may not be. And without harm simply means, let's say, this, imagine this way, like, I have all the electronics inside, it has the power dumping component, things are working, things are fine, but nobody actually tests the tester itself properly, and the chassis becomes too hot. That's not acceptable. The chassis should not be hot. Like, if it should have a very clear marking, air comes in, air goes out, and the chassis should, again, it will be like hot. It should not be like, oh, it deep fried my hand. So all those things have to be designed very thoroughly, and this part surprisingly sucks in surprisingly large amount of devices. Like, they never actually sat down and properly designed. It's like, how the heck you gonna move that much air? How the heck you gonna dump that much heat into the air? And the only solution everybody can come up with is like, what if you put a super duper hyper high RPM fan? I'm like, what if you learn from PC industry and put big ass fans with giant heat sinks? Again, quality ones do, cheap ones don't. They rely on like brute forcing a lot of air, and that's why like people are like, it sounds so much. Yeah. So you have to find a way to dump all that heat safely and efficiently. And ironically, I have not seen anyone that is water cooled. It will be perfect, especially in places, European places where people need heating. That will be like, whoa, hot water, awesome. And water can take a lot of heat before it actually heats up. Your basically water heater, storage tank water heater could easily eat up 5 to 6 kilowatt, like, so more than good enough. And you need a good high precision measurement method, because without measurement it's not that effective. Because, for example, if you have a good measurement, you know what happens to the battery pack if you're drawing the amount of current that you designed it for. Let's say you are like, hey, this is cool and awesome, you bought a cell and you're like, hey, what if I draw 5 amps? On paper it should work, but when you actually test it, you were like, wait a minute, voltage sag is more than anticipated. The seller could have been tricking you. That sort of things have happened. So for this reason, you need high precision measurement. Now, high does not mean like absolutely ultra high grade, metrology grade, but you are looking into something that should be reasonably high precision, so to say. And onboard data logging or PC's applications are desirable. Those are extra plus. That allows you to do automated system testing and all that jazz. So that's the logic behind it. A device that adjusts its own parameters, like how much current it draws, how much voltage it draws, or whatever it needs to do, the airflow and all that, it does everything based on itself, based on your input. Like, it's like, I got this, what do you want me to do? Okay, you want me to do that, this is how I'm gonna do it. How, it's onto its own microcontroller, but what you need to do, the user will tell it. Stable way of dumping that heat continuously. Many of these devices are used in production environment where they could be running on for days. Like, again, power supply one testing, let's say the testing regime is, let's say, 6 hours. Then it does not mean they turn it off. It simply means, okay, the power supply goes again, new power supply comes in, now that you test it again for 6 hours. So it could be running 24/7. It has to be designed such a way to handle that heat load. Basically a giant room heater at that point in time. And high enough high and good enough precision measurement so it can notice deviations within reason. And data logging and PC apps, these makes things far more comfortable, far more convenient. Otherwise you can just have something like this where it's just like, okay, a number shows up, like what is the cell capacity. Again, that's more than good enough if you have nothing, but sometimes a bit more love is needed. So what about designing it? Well, designing wise, you have a very basic start, power resistor, like something like this. Like, it has resistors. That's the primary system here. It controls how much amps goes to it, the resistor, and that's it. So resistor becomes the dump load, like this. These things are very good, very low cost, and amazing for big bulky power loads. For example, if you have to test a solar panel, and solar panel could be huge, let's say some solar panels can easily dump 600 watts of an electrical energy on its own. So how can you dump that amount of power cheaply? Huge ass resistor. Now be mindful, these sort of resistors should never be exposed to the air. They have to be exposed to a casing. Now the casing is reason because these things do get hot enough. If that touches human skin, you're dead. So again, these are cooker level heat. So you have to have a containment unit around it, and generally good powerful industrial fans so they do not cause damage to themselves. Again, many of them can handle very high temperatures, as in like 500 degrees Celsius. But you may not want a box whose inside is like, 500 degrees Celsius hot. That's why I say safely and efficiently. So simple power resistors are a very good starting point. If you have nothing, you had no way of tangibly knowing anything, start with power resistor. That's good enough, gets the job done. And many scenarios, people literally rely on this. Industries run on this. These are industrially manufactured. So there's a need for this, there is demand for it, and it's a good start. Then we come to the big boys, or should I call expensive boys. MOSFETs, these puppies. Now, these are generally desirable for high amps. Like, do we need high amps? Let me give you an example. This is a puny power supply by modern standard. I bought it like 15 years ago or something. Cooler Master 500 watt power supply. Now, here's deal. It has 12 volt voltage rail. That's why I have two of them. It has like 18 amps. 18 amps of 12 volt. That's a lot of amps. Now, that's not the highest amp rating on single rail. Go to 5 volt, this puppy can dump 25 freaking amps in 5 volts. That's bonkers. You do not even want to look into the amp capacity of modern power supply that are like multi-kilowatt, like 2 kilowatt power supply that you can buy for normal PC. Yeah, that's 150 amps on 3.3 volts. Yeah. And do not dare to look into what happens into server power supply. That's like, bro. That's like, bro. Like that can, cause overheating on these puppies on low voltage rail. So brutal amount of amps are needed sometimes. In those scenario, MOSFETs are, I'm your guy. These puppies can handle that. And it generally does not like the idea of super duper hyper high voltage. Nowadays that's not an issue, but if you are testing something very high voltage DC, let's say you are testing 800 volt DC, you may be a bit apprehensive. It's not like it cannot be done, it's just like, you sure about that? Or let's say you are working with solar inverter setups, those puppies can go to 1500 volt DC. That will be like, whoo, you were like, whoa. However, all that's the amp capacity with the fact that it has high fast switching. Now, fast switching is very critical for simulating transients. Transient is the most brittle, hard part to get in right. Let's say you built a power supply. Again, you may be like, hey, what if I put a lot of capacitors, I'm like, go, wabam on it. So it can handle anything. Here's the deal. It should not handle anything. I give you a simple example. NVIDIA made RTX 3000 series core. Now, either they rushed it or they underestimated the power drain. Those cores, like the actual silicon, they were consuming power way too much. Like they were like, whoa. So 400 watts to 600 watt power draw. That power draw itself is not an issue. It's like, okay, you want this much power, we give you that. Surge happens. Again, we were expecting this sort of things. It is a common thing. You have milliseconds of surge. Surge in RTX 3090s could go stupid level, as in multi-kilowatt surge happens. Now, these surges are very short. Now, if you have a very crappy power supply, it will actually stay on, but it will damage something, either in itself or something in the component. If it's a good power supply, it will be like, bro, no, it will turn off. And you may not even know why the heck your system turned off, because nothing is smoking, nothing is on fire, as it should be. But that's a transient situation. You must test your equipment for transients if it's supposed to handle that. Again, realistically, everything's supposed to handle it. So you need fast switching in those sort of scenarios where you can be like, hey, everything is drawing, everything is calm, and then you're like, wabam, what if I'm like drawing 30 amps? Again, based on your spec sheet, do you want it to keep working on 30 amps, or you're like, bro, chillax, let's shut it off? That's up to you. You need a way of switching it quickly. So that's why this is a desirable fact, MOSFET. And again, it also allows you to do age testing, how quickly your components are wearing out. And yes, resistors do wear out, capacitors do wear out, diodes do wear out, MOSFETs do wear out. Like these things have electrical limitation. So if you're putting a lot of surges into them, it will wear them out. And that's why ATX 3.0 power supply has a very serious rating on basically surge. Because again, they are designing in such a way that you can turn it on and off day in and day out. It should not cause an issue. And IGBTs are used sometimes. I'm not saying way too many times, but sometimes they are used because they are desirable for high voltage. So if you're like, I'm dealing with some high voltage puppies, I do not know what the hell you are doing that you need that kind of high voltage DC, because Other than HVDC, what else is there that is in between, let's say 1500 volts and million volts? Like, what is in between? Like, I do not know of any tech. Again, if you know, please comment down below. If you need that, these are still desirable. However, they are a bit complex and generally not preferred, and MOSFETs are far more desirable nowadays because apparently MOSFETs are getting very high voltage ratings now, and there are companies that are manufacturing MOSFETs specifically for power load. So they are like, bro, I got this, I can handle like serious voltage. So that's there. Now you may be like, why the heck go through like MOSFET or IGBTs rather than just having multiple resistors? Well, issue is control. Going through all this complexity, you're like, okay, you have a power sink and then you have a material that dumps heat into it. Why the heck you have another power supply and another microcontroller, another logging mechanism, like all the complexity? Why do you have that? Well, complexity is the enemy of reliability. That is a factual thing. However, it does give you something. That something is control. You control how it happens. Like trying to do resistance control, it's very difficult. Now again, you're like, hey, I know this is, again, that's awesome. Build a dumb resistor. That's why they still exist. But if you are changing it, or if you are changing different equipments, you may require different setup. At that point, it's like, just buy this. So that's why there are designs of it, multiple of them. Most of the time, focus on either simple resistor one or MOSFET ones. Now, can you build it yourself? Do it yourself? Short answer, yes. Basic dump loads are very easy and very easy to get started. If you have nothing, that's a good start. Just, this sort of registers. Nothing awesome, but like good to get started. Better than knowing nothing. You will know enough that you're like, okay, I see what's happening. So that's good. And if you can monitor it, as in like the voltage and voltage drops, that's still useful. And then you have the desirable, the honey baby, that is linear power MOSFETs. These are the backbone of almost all industrial setup based systems. Now, how can you drive it? That's the issue. The MOSFET is not that expensive. Building a circuit is not that expensive. Is how the heck you control it. To control it, you have basic analog circuitry, meaning you have op amps and basically resistors, feedback loops and all that. It's very simple, very few components, not even 100 components. You can achieve this in very few components. It does work. It's a good system. It's a very good point, but it does not have too much control and viability. However, then you can take the same concept, you still have linear power MOSFETs, you still have feedback control. Now you add complex digital technology to it, meaning you have a microcontroller who's maintaining and measuring all other things. Things can get out of hand in terms of complexity, but it will allow you to do more. For example, many times people add 16-bit analog to digital converter, because if you do not have that, the voltage drop between, let's say, a resistor, power resistor that you are using to monitor it, it would be so low that the result 8-bit analog to digital converter that is in Arduino, let's say, it's not high resolution enough. It will not give you precise enough measurement. So people add this sort of thing for precision measurement, and better the measurement, the better the feedback control. So there is a reason for going with that high complexity, and it's a very good complex project, but you have to be a bit more mature, a bit more capable to get this run. Analog basic feedback loop, that you can do. Complex digital ones, that do take some horsepower, let's just say. That takes some serious horsepower. But it can be done. You can start with basic dump loads, and then you can go into linear MOSFETs. Then again, complex digital feedback loop, that will take some horsepower. I have linked some videos down below, and that's a rabbit hole. Let's just be very clear about that's a rabbit hole. It keeps going down. So it's up to you. What about buying it? Well, buying it gives you few options. Simple, like right out the gate. Constant current, that's awesome, as in like how many amps you want, you can control it. Constant voltage, that's awesome. Constant resistance, meaning that's why I said like the user sets the parameter and it controls what it needs to control. So it will take the ohms value. You give the resistance, okay, it takes the ohms value and adjust voltage and current based on ohms law, and then it's gonna like, okay, I need to increase this or decrease this to achieve the required resistance. That's awesome. And then we have power. Now, to this day, I do not get it, like, I current rating, V, voltage. Why the heck there is P? R is for resistance, that's awesome. But why the heck there is P? It should be W. Like, power has a word known to it. Watts. In electrical world, we have power is represented in watts. I never see W. It's like always weird to me. So, like, there is a symbol to it. It's like W. We have that. Use W. So watt setting, and that does require that voltage and amps feedback loop. That's why you need complex circuitry to achieve this watt. So you could be like, hey, I'm building this battery pack. It's providing a controller circuit. That controller is managing it on its own. So controller can work in a different magnitude of voltage. It could be like, hey, fully charged voltage is like, let's say 52 volt, then it drops to 38 at the lower discharge level. It can work in that voltage range. You will design it that way. However, it will draw same amount of power. It will like, oh, the voltage is dropping, I'm taking more amps. It will compensate. So you need this sort of constant power mode to simulate that. It's like, how the heck, because that literally means your battery bank could reach a point where it's like, hey, I'm actually low on power, but I'm actually giving more amps. So again, you need that constant watt system. So you have a lot of choice. You can start with like very cheap units, and daddy units, something like this. And this is why you need like PC power supply, and God help you if you have to touch server power supply, it requires sometimes even double than this. If you ever see why the heck there are so many modular power testing unit, that's the reason for that. Like, again, you can easily have a system where you have like hundreds of amps on a very low voltage, while each of them can easily handle the wattage, as in like 1 kilowatt. That's easy, but they will be like, hey, I can only handle 10 amps, my man. Like amps and volt rating, they are separate. So total power, you may be like, hey, it's 100 watts, so that means I can give 1 voltage and 99 amps. Yeah, that's not as gonna work. I know. It's like, you get the point. Like there is a limit to voltage and there is a limit to dielectric strength of the electronics used. So voltage is also limited. So generally you design for voltage, and amps you parallel it. So this sort of, and be mindful that this sort of power draw, wires do not work. You have to go to bus bar and you have to badang, 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 badang. I mean, like, imagine how thick these puppies are. So you can go from very cheap units to very bonkersly expensive, meaning your college university fees will look free compared to that. That's how expensive these puppies can get. And then you have the cream of the crop, that is programmable DC electronic load. Now this is the thing that I have not seen too many DIYers building it properly. It can be done, let that be very clear. It's not law of physics that it can't be done. It's just that very difficult to do. Heck, because the feedback control has to be almost at oscilloscope level speed. So it's difficult. And benefit of this sort of programmable DC load, it simulates how the heck your appliance will behave. Again, you will design it, but that's the whole point. Let's say you are designing a motor driver unit and it's draining power from BMS of a car battery. That's 400 volts. So 400 volts DC bus, and your amps draw could be bonkers. Or it could be in reverse, because again, regenerative braking, you need a way to simulate that. Programmable. And programmable also allows you to do automated testing. Many of these programmable units have a COM port where you can communicate with it and have a whole ecosystem where it's like, check it, awesome, check it, awesome, that's all, check it, not awesome, yeet, check it, awesome, go. So that's up to you. That allows you to have a complex testing, and it's necessary. That's the difference between like same company, same goddamn factory, giving you very cheap products and very idiotically expensive. Like some companies whose sole job it is, I'm not even making it up, they buy cells, lithium ion cells, like these sort of cells from, let's say, Sony and LG and all, Panasonic, and what they do, they buy boatload of it. And then they test it. They keep filtering it out until they find a batch of cell that is very close to each other, like in terms of actual electrical testing. And then they sell those packs to satellites. Now you're like, don't satellites have very high grade BMS? Yes, very high grade BMS packed with very high grade cells equals very high reliability. You do not want to be in a scenario where it's like, if the cells are garbage, the BMS will kick in. No, you're like, cells are awesome, BMS are awesome, then we have another failsafe that is awesome. Then you trust what we call triple redundancy. Then it's like, okay, we got this. Now only a cosmic ray can cause boom boom event to it. It should not go boom on its own. So same goes, complex testing is required. So DIY is also a good option. Buy is also a good option, especially on large units. You're like, dude, just buy it. And again, please tell me if any of you have seen any unit that does anything higher than 1500 volts and DC, and anything that does water cooling. I do not get it. It's like, why the heck they do not have water? It's like, it's far more efficient, less noisy. So this was my presentation on DC electronic load. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.